Welcome to Chapter 12. Chapter 12 is on kinetics. It's maybe one of the first big chapters of AP Chem that is completely new, nothing that you've done in first year. That's exciting, that's a good thing, that's what you've been waiting for, right? So far, we know everything there is to know about stoichiometry, right? Stoichiometry deals with quantities. How much reactant do I need to produce a certain amount of product? How much reactant might be left over after the reaction goes to completion? That's very important to know if I want to make chemistry valuable in the real world or here for commercial use. I need to know about the reaction stoichiometry. How much do I put in? How much do I get out? After spring break, we'll talk a little bit more about energies. So this would be something that's important for a reaction to run as well. How much energy do I need to supply in order to get a reaction started? Or when a reaction is running, how much energy is produced? Is it endothermic, exothermic? We're going to focus on reaction rates in Chapter 12. Kinetics is the study of reaction rates. How fast does a reaction go? Which again is important in real world and industry. I want to make as much product as possible, so what can I do to make that reaction run more efficiently and run faster? So we also need to learn about the steps that might take place in order for us to get from reactants to products, which is called a reaction mechanism. We'll look at those later. For now, we're going to look at how to set up a general rate. Super easy, it makes sense. So we've got this equation. We've got some nitrogen dioxide that decomposes to form nitrogen monoxide and oxygen gas. We're going to study the change in these concentrations over time as this reaction takes place, and we're assuming that it occurs in a closed container. Okay, this makes total sense, that a rate should be like a change over time. You know, you might think about rates in terms of like speeds or velocity, a change in distance over time. This will be the change in concentration of a particular reactant or product over time. The concentration could be measured in moles per liter, or they might just use the symbol big M, there it is, standing for molarity. Either of those would be acceptable units for concentration. And we should make note that they're going to use this symbol a lot, this brackets. When something's in brackets, now usually that'll be an element or a compound, the brackets refer to their concentration. Molarity, moles per liter. Change in concentration over time. So let's look at some data for this reaction. Wow, this is excellent. We want to look at the average rate at which the concentration of all three substances, reactants and products, how do they change over the first 50 seconds of the reaction? So we've got both graphical data, which is fabulous, and they've got this cute little data table for us. So let me refresh my memory. The reaction's up on top. Here it is. And oxygen's kind of hanging out down there. 2 nitrogen dioxide decomposed to form 2 nitrogen monoxide and oxygen gas. First, let's focus on the data in the table. So if I want to do change in concentration over time, let's start with the reactant, nitrogen dioxide. This is over the first 50 seconds. So over the first 50 seconds, here's my change over time. Now technically this should always be final minus initial. So I will have something that looks like this. My final concentration, 0.0079. And again, I could say molarity or moles per liter minus initial, 0.01. They've got it listed as moles per liter, but again, capital M is the same thing, right? Over time. The time's going to be 50 seconds. Excellent. Right away, notice that this is going to be negative, and that is okay. So we plug this in our calculator. We'll go a few sig figs. Let's say negative 4.2 times 10 to the negative 5th. Now for a unit, you could leave this as molarity per second. That would be fine. Or you might see this as moles per liter second, which is totally fine. That's like molarity per second in a sense, moles per liter second. Either of those are acceptable units. Well, that makes sense, right? Okay, so now let's do the other ones. Let's do the products. How about NO? Nitrogen monoxide. Change in concentration over the first 50 seconds. Okay, so initially it's 0. That makes sense. It's a product. Initially it's not there. Final concentration is 0.0021. Minus nothing, which I'll leave, over 50 seconds. Okay, so we plug this in our calculator. Da-da-da. Interesting. 4.2 times 10 to the negative fifth. And again, I don't care which unit you want to use, as long as you put a unit in. You could use molarity per second or moles per liter second. All right, so there's one product. And now let's do the same thing with the last. All right, my oxygen. Final minus initial, O2 oxygen. Final concentration, 0.0011 molar. Initial is obviously 0 since it's a product. Over 50 seconds. This isn't bad, is it? Plug this in my calculator. 2.2 times 10 to the negative fifth. Change in molarity per second. Piece of cake, right? Like super confident about this new chapter, huh? Change in molarity per time, reaction rate. Now, a couple things that are interesting. Let's look at the ratio from the balanced equation. There it is. 2 nitrogen dioxide form 2 nitrogen monoxide plus oxygen gas. Look at the ratio from the balanced equation and look at the ratio between these reaction rates. They change according to the ratio from the balanced equation. So that NO, nitrogen monoxide, that's formed at the same rate by which the nitrogen dioxide is consumed. They're the same ratio in the balanced equation, so the reaction rates are proportional. They make sense. The only difference is that we have a negative reaction rate for that reactant, the nitrogen dioxide, which really just means that the concentration is decreasing over time. They're changing by the same rate, but the reactant is decreasing in concentration. The product is increasing. Interesting. The oxygen makes sense. It's half. It's produced at half the rate at which the original reactant is consumed. It's produced at half the rate that the other product is produced. They're proportional to the ratio in the balanced equation. The only difference is that technically a reactant is going to come out to be negative. Now you might not always see it that way. If you see a reactant reported as a positive reaction rate, it's just understood that if that's something on the reactant side, its molarity is decreasing over time. So sometimes the negative will be left out just because it's understood that we would know that a reactant should decrease in concentration over time. The products will always be a positive. They're increasing in concentration over time. Now the other kind of interesting thing is if we look at this graph. If you look at the graph, check out this guy, the nitrogen dioxide and the nitrogen monoxide. They have like the same curve, it's just inverted. Oh, yeah, because they're changing at the same rate. But the reactant is decreasing in molarity or concentration, and the product is increasing. And if you look at the oxygen, it's increasing in concentration over time, but at a rate about half that of the other product. So the graphs are proportional to the ratio in the balanced equation, and the numerical reaction rates should also be related to the ratio from the balanced equation.